All right. Hey guys. So any question you like, just say them up and then either speak up by turning on your mic or you can type on the chat either way. Yeah, go ahead.
Professor, I have a few questions.
Yes.
In regards to the until operator, once we found phi2 to be like satisfied, does it have to continuously hold or?
No, it doesn't need to be. So the
Okay.
question was, okay, let's I think that's nice to clarify this a bit. I think for that one there, if you can refer to, okay, so this one here, let me show to you where you can look at. So if you go back to the lecture on Thursday, so this was kind of like a beginning, the beginning visual summary we did about the three operators, but until operator over here. So the idea would be once phi2 over here is satisfied. So this point here correspond to, if you go to the formula here, so there's an until formulation. You can see there exists certain point where phi2 is actually satisfied, but the formula does not require any further about whether I+1, I+2, and etc. should really have phi2 satisfied. It doesn't say, so that means you don't really need to. So you just have to make sure phi2 over here is satisfied, and also at least until I-1, phi1 has been satisfied, starting from 1 to I-1. So your question was, should phi2 should still be satisfied over here? It doesn't really matter. If you already got this and this satisfied, until will just be true. So having phi2 starting from this point, either satisfied or not satisfied, is not going to change the result.
Oh, okay. And I also have another question in regards to GF operator. You did some examples in class, and I also was rewatching the recording today, and it was, if you can like go to that example, like I can.
Yeah, sure.
That would
So
be
you mean
great.
the lecture, the example we did on in class?
Yeah.
Okay, sure. Is it this one here?
Yeah, it's this one actually. Yeah.
Sure. Which one?
I was just the first one.
The first one. Okay.
Yeah, this one. I was just wondering, you were saying the only path to consider is S0, S1, S0, S1. And I was just wondering why just that path if we have to consider like all the path in like model.
I see. Yeah. So thinking this way. So in order for this implication to be true, and let's go back to the basics. We said that in order for implication to be true, then we have to make sure antecedent is true, and also the consequence is true. So one strategy would be, what does it really mean when the antecedent over here is true? So here, this is saying infinitely often we got P being satisfied. So that means it cannot be this pattern over here, because this one here only has P satisfied only once. And once you get stuck in S2, you're actually going to get stuck infinitely. So P will never be true again. So if you look at this diagram here and look at this constraint, so that tells you in order for P to be infinitely often true, it's got to be this particular pattern, in which case we get starting from S0 over here and go to S1, go back to S0, S1, go back to S0. You wouldn't even actually at some point go to S2, because once you go to S2, you're not going to have infinitely often P anymore, because you should continuously be able to find the future point. So Sarah, are you okay so far about the antecedent?
Yeah.
Okay, so that's a critical point. I would say this is a kind of nice strategy. So especially for dealing with the implication. Sometimes the antecedent for the implication might suggest just one single unique path pattern. In that case, you would just have to consider this one. And then assuming that this is the case, is it the case that GFR is actually true? Indeed, it is, because it will just alternating, the states between S0 and S1. So R will be infinitely often true.
Oh, okay. So just to sum it up, we have to look at the path that will satisfy G of F P, basically.
Yeah, this in general, of course, may not be unique. It could be multiple, in which case you may have to consider multiple patterns. But in this case, this system here, we're lucky, only one to consider.
Oh, okay. Thank you so much.
No problem. You said a few, so would that be it, or you got more?
Can we just go over the until operator, because I'm getting so confused when I was trying to like do the practice questions.
Until operator, you mean the definition, or you want to look at the questions?
like an example of it, just like how we
Sure,
would like.
sure. Okay, sure. Yeah, so until operator here again, I think that you'll be the most useful if you can maybe after the session, I would say we can talk briefly. So this is until operator, right? So this
Yeah.
basically is telling you, so if you say phi 1 until phi 2, so we are requiring that phi 1 should be true since the beginning until certain point, so that'll be I minus 1. The next point will be the I. So this is where phi 2 should start holding. So that's really the definition. Of course, you can also look at the quantification. So are you okay in general about the definition for detail?
Yeah, okay.
Okay.
I'm okay with the definition.
Okay, sure. So let's look at maybe look at one of the example we did on Thursday. So let's see this. Okay, let's say, for example, here. Let's say this one here. And we have the starting states as 0 over here. And we say P until R, right? So over here, so well, of course, every example might be a little bit different. So you have to be kind of focus more on the path pattern. So in this case, starting from S0 over here, we can either branch out to here or we can branch out to here. Either way, right? There's no third way to branch out. That's number one.
Yeah.
And from here, we know that you can either branch out to S1 or we can branch out to S2. And we claim that only by looking at these two prefixes of the path already, we know the P until R is satisfied. But let's see how. First of all, you can see this S1 and S2 over here, like an S1, S2 over here. These are the two future points where R is actually true. So we already satisfy this particular condition because we find that future point for each path where phi 2, in this case, R is actually satisfied, right? This one here. Are you okay so far? Just about satisfying
yes.
R. Okay, good.
Yeah.
And then according to the definition, our R over here happen to be just index 2, index 1, index 2, and also index 1, index 2. So if we go back to the definition here, the second one is saying, given the I for your individual path up to and including I minus 1, you should have phi 1, in this case, P satisfied. So let's see if that's the case. So here, since index 2 is here, so the only thing we want to look at will be from 1 to 1, index 1, basically. So now S0, in this case, does it satisfy P? It does. So it's going to satisfy.
Okay, but like, let's say S0 doesn't have P, then it doesn't, like, this would be false then, right?
Yes, correct. So if you don't have the P
Okay.
over here, of course, that will be different. Yes. So you want to think
Okay.
about whenever we talk about until over here, in some way you have less to check because in order to make it true, you have to, number one, find the witness states that's going to establish phi 2. And then you want to find that starting from 1 until I minus 1. For all these previous states, they must have the phi 1 over here satisfied. If you don't really have either of the option over here, either of the condition, in that case, you're going to have this being false.
Oh, okay. Okay, thank you so much, Professor.
Okay, good. Okay. Okay, I can see some hands raised. Didn't really keep track. I will just go by how you appear on your chat. Okay.
First.
Oh, you were first? Okay. Vanessa, go ahead.
Yours first. No, Hashir was first.
Doesn't matter. That's okay. We'll handle all of you anyway. So Vanessa, go ahead.
Oh, okay. For question 3 on the practice questions thingy.
Mm-hmm.
Can you just go over why the correct answers are true? Like,
yeah, we can do
I
that.
didn't really understand the question.
Okay. Okay, let's take a look. Example here. Okay. Okay. Question number 3. Oh, this one here, right? Okay, I'm glad you asked. So I think this one is something a little bit implicit in your lab number 2, because your lab number 2, a big part, of course, is about how you write the algorithm in Pascal. That's one thing. And the second part, which is equally, if not less, if not more important, it should be equally important, which is to write post condition that should be both correct and complete. Okay, so let me talk about this a little bit, because I'm sure you will get some question on Tuesday. Okay, let me talk about principle first, and then it will be much easier to actually understand what's going on over here. Okay, so imagine this. Okay, so sorry, my Apple Pencil has been disconnected. There we go. Okay, so just consider any algorithm. Okay, and as I said in the test guide on Tuesday, you will not be required to write any code in Pascal, but you might be required to read the code that's given to you in Pascal, okay? Like in this example question. Okay, so the idea would be, let's say you do have some implementation over here, and of course, you have the input value, and also you have the output value, right, conceptually. And of course, eventually, over here, the last value that's been set to the output, it will be conceptually returned by the algorithm. So the post condition conceptually is really going to relate the input you're given and also the output that's last set for your algorithm, right? So let's get this one straight first. And of course, here I'm just putting one input variable, but in general, you may have multiple input variables. But I would say output variable usually just one, usually, okay? So this is the last set value, okay? And the post condition will just be the assertions. So here I put plural, meaning that in order for the post condition to be complete, sometimes you might need multiple, not necessarily just one, okay? Assertions relating the input and output. So Vanessa, are you okay so far about the concept?
Yep.
Okay, good.
Yep.
Okay. Let's now say, let me sketch. Let's say if I got only a single post condition, if I say assert, okay, and then I put something over here. Okay. Let's say this is the only post condition. In some way, we are isolating it, okay, just post condition. Okay, now the big question is this post condition correct and complete? And to really judge that, usually, well, this is also how we graded your programming test 1 and possibly programming test 2 as well. So the idea would be, we will give you some input and output pairs. Okay, so given a correct pair of input output, the assertion should pass. Otherwise, if you fail on the correct input and output pair, that means the assertion is not good, right? Another scenario would be, given an incorrect pair of input. I'll give you some very simple example in just one moment. Output assertion should fail, right? Let's just see one example here, okay? So let's say the input over here, just for example, the input here is just a tuple of integers. Okay, and then the output over here is, let's say, a tuple integers, a tuple of integers sorted in non-descending order. Okay, let's say that's an input and output. Okay, And then let's say the assert over here. One example could be, we simply want to say it's sorted in the ascending order. So something like, for every, let's say I, and then I should be in 1 until the length of the input or the length of the output, doesn't matter. Okay. And then colon. I think it should be -1, but anyway. Okay, and then over here, colon, we're going to say the output I, let's say less than or equal to output I plus 1, right? It's a very standard, post condition for the array in the output to, for the tuple array output to be sorted. Okay, let's say this is the only post condition we are having for this algorithm. So the question is this post condition itself really complete enough for our purpose of asserting the algorithm being correct? Okay, so let's say this. The way to test it will be 2 ways. For example, if I give you, let's say, input over here, let's say if I simply give you, let's say 5, 3, 1, and 2. And then the output over here, if I give you something that's correct, 1, 2, 3, and then 5, right? So if I give you this particular pair and then run this against the assertion, it should pass if the post condition is correct. So Vanessa, are you okay with this one?
Yep.
Okay, that one's good. Okay, the trickier one might be the second category. Okay, so given something is incorrect, in that way assertion should fail. But let's see if that's the case. Okay, let me say if I give you input over here, let's say 5, 3, 1, and 2. All right, that's unsorted. And if I give you output over here, let's say that one there, I give you, let's say 23, 46, 69, 92. This apparently is wrong because given this input, the corresponding sorted output tuple cannot be this one, but it will satisfy the existing post condition because the existing post condition only asks you to make sure the output array is sorted. So this one is supposed to fail, but it actually passed. So this can really demonstrate that this particular post condition is not appropriate. Okay, I'll write it down and then to see if we got any follow-up. Okay. The assertion should fail on this, but it actually passes. So this illustrates that is actually inappropriate. Are you okay with this example? With here?
Yeah.
Okay, so hopefully this kind of illustrates to you. Okay, let me just recap and then we can look at that example question. So now it'll be easier. The goal would be we are given some algorithm and we don't really show the detail. We're just saying that we just want to test whether or not, given the input and output by the algorithm, if the existing post condition over here, let's say in this case just 1, is it enough and correct for us to use this as a single post condition? It turns out this is not, because if you're given any invalid input and output pair, meaning that the input itself is okay, but output has not been computed properly. As apparently you can see this one, even though it's sorted, but none of the elements come from the original input. So that's not appropriate. In that case, anything that's not appropriate, the assertion should really fail to signal the error. So that's really the second category. Okay. So now, before I ask any follow-up, let's now take a look at the original question, right? So now here, let me also try to talk about the big picture. Okay, so the algorithm we are considering is we have a single tuple of integers, could be empty, and then it's going to output another tuple, and that one there is going to only keep the positive numbers in the input. For example, if you got the input being here, right, we're just going to filter out -2 and also -4 and also 0. only keep the positive numbers. So that means we got 1, 2, and 3. Okay. And then, so this will be just describing what the algorithm should really do as expected. And let's say now this is the only post condition for the algorithm, right? And is this really correct? What does it say? It is saying that every element in the output should just be positive. It's similar to what we said earlier. We say every the output array should just be sorry, lost the connection again. Give me a moment. Yeah, so this this post condition here only says the output array should be sorted, but doesn't really say every element here should really come from the original input array. So it's kind of similar mistake, right? So in this case, if we go back, let's check to see the options over here. Okay, and of course this one should not be chosen. It's not appropriate, right? And let's take a look at this. This one here, the post condition is inappropriate because it only consider just the array being containing all positive. It doesn't consider anything like the elements in the output should also come from the input. That's what's missing. And this one, okay. So the post condition is inappropriate and can be illustrated by a test. So let's see. Let's say this is the post condition. And this one over here is, sorry, let me say it again. This is the input over here. And this is the output. Okay. And now if this is input and output, is the output correct? Not really, because you can see if we want to keep all the positive elements, we should really get 1, 2, and 3. But this one has empty, right? But this one here, that means the correct or appropriate post condition should really fail. But this one does not fail. When you are actually having some incorrect input and output relation, that can be passed by the post condition. That means there's something wrong with the post condition. So that's why this one here should be chosen. Vanessa, are you okay with this option here? I think others are kind of similar, but let's make sure you got it.
Yeah, I'm really, I think everything, like the other output examples 1, 2, and 2346 are like straightforward. Like I understand, like given your example and whatever, why those are also what like fall into the same category of correct.
Yes.
The only one I don't get is the one
Yes.
with -2.
-2 over here.
Yeah, I don't understand why that isn't correct.
Okay, that one there. Okay, so, okay, good. First of all, we understand. Oh, let's. There are two things to consider. Number one, this output here apparently is not correct, right? If the output is not correct, okay, let me just take a quick look. The output over here is not correct, but somehow it will.
Isn't it because there's a -2 in there?
Yeah, -2 is definitely the key, but let me just be sure. Okay. So if the input, if the corresponding output is not correct, then we'll definitely expect the post condition over here to actually fail. Right? That's definitely something we'll expect it to fail. But the problem is, yeah, this one could be a little bit tricky over here. You know what? Let me make a note on this one. So Vanessa, is that correct? This is the only one you're confused? This one here?
Yeah.
Okay, no problem. How about this? Let me, I will take note of this one. Let me check a little bit more carefully, and then I will update the description over here to explain a little bit better. And then that should be done a little bit later tonight.
Okay.
Okay?
So just can I just ask?
You can
like,
ask. Yeah, sure.
Okay. So is the reason that it isn't correct because like the output is incorrect, but the assertion will also fail, right? Because in the other cases, the whole point is that the output satisfies the post condition, but it's still not correct.
Yeah, the output is not correct for sure. And then you actually want actually the post condition also failed.
Yeah,
right?
and that's okay. Like that's a sign that it
maybe the
is
wording.
appropriate.
The wording will have to be improved. I agree. So here, okay, I tell you what a tricky thing is. I may have to modify the wording slightly. What we know for sure, number one, the output here is not correct, for sure, number one. Number two, if the output is not correct, we would expect the assertion to really fail. In this case, it does fail, which is also good. But somehow, this assertion would be considered as correct as far as this output is concerned, right? Because it can catch the error. So I think
so it's not an answer because the post condition
yes.
is appropriate for this
that's correct.
example.
I think you got the essence of that, but I think that my wording should really be changed a bit. I can see there's some slight confusion over here. Let me look into this question because you will get something similar on Tuesday's test. So I may have to change the wording a bit to make it more explicit.
Okay. Cool. Thank you.
But I think what we discussed, you can assume that's actually right. But I think that just the wording of the question itself can be improved a bit. I think I will do that. Okay. All right, guys. I think for this question here, it's a new type. That's why I kind of put one example here. So just have to remember this principle over here. When your purpose is to test about whether or not the post condition is correct, you have to make sure if you give the correct output, it should really pass the assertion. If you give the incorrect output, it should really fail the assertion. That's the principle, right? Okay, Hasha, go ahead.
Could we work on doing a couple of nestings of LTL operators that I tried on my own and see if I got it right?
I would say that one, if that's very specific to your own example, I would say, let me answer other question first, because I'm not too sure how much time you might take. Alternatively, you can maybe come to the office hour later, then we can deal with your specific question. Why don't I take other, is that the only question you have?
Okay, well, I mean, I worked on these with other people in the class who were present in the call too.
Yeah, my point is, we better maybe work on some more common resources that were given to everybody first. Then if we have time left, we can definitely look at it too. I'm just saying, if we don't have enough time, we can maybe deal with that, maybe offline. So in addition to that nesting question, do you have others?
Yeah, sure. I'll ask a general question then.
Go ahead.
Are there some nestings that are syntactically correct but illogical to actually perform on a trace?
Sorry, can you say that again? I want to make sure I catch you.
Are there some nestings that we can write syntactically that would be correct, and we could write a correct formula quantifiers, but they won't be possible to draw on a LTS?
Not really. I think okay, so here, okay.
For example, if I ask global phi one until phi 2.
Yeah, I think okay. So when you talk about syntax, right? So syntax back to many lectures ago, when we first talked about how you can derive, the formula based on the grammar. Okay, so I would say any syntax that's derivable from the grammar. That would mean they have some formal meaning, should exist. And the formal meaning should be according to, the quantifier, semantics that we talk about in the class. And I think whether or not the actual formula is actually correct or not, it kind of depends on what idea you want to express. If you remember back on Thursday's lecture, right? We said that, the phrase like I smoke until I was 22. Then we actually consider two things. One is, I think I smoke until I was 22 versus I smoke until over here, 22 and globally not smoke, right? So we kind of consider these two. Both of them are derivable from the grammar. But as far as that particular English sentence is concerned, this will be considered as correct, but not this one, right? So the formula itself wouldn't contain any logical error. It's about which expression you want to use the formula to formulate. That should be the context. Does it make sense?
Yeah, I understand that. The reason I asked is because I was working with combining for example, the global operator. So I would write global and then bracket phi1 until phi2 close bracket. And I just the meaning of it, I wrote it down, I think correct, but it didn't make sense to me.
You mean this one here, global and something until something?
Yeah, phi1 until phi2.
Like this, right?
Mm-hmm.
You can think about, well, of course, to really figure out the formal meaning, you will have to say this one here is going to be a sum for all, right? For all I, basically for every states in your for every index of the states, this until should be true, right? So this is a little bit like an infinitely often, like a GF idea, similar. This is to say for every index I, you should be able to find some satisfaction of phi2 at some future points. And then before that future point, phi1 should always be true. If you didn't have the G, so that means you only need to find a single future point that will satisfy phi2. But now if you actually put a G into place, that means you should be able to continuously find the future point that satisfies phi2. And before that, phi1 should also be satisfied. Do you see my point?
Okay, yeah. So in general, there's no combination or nesting of operators that's syntactically correct, but
it doesn't make logical sense. No.
Yeah.
And the short answer is no. But I think that this one here is actually a very good example. This one here, you can think about, compare that to, okay, I shouldn't say it's not equal to, of course. I would say compare. Compare to infinitely often phi. They're somehow similar. Let me say it again, so for those of you who kind of didn't quite follow. If I didn't have the G, I know that in order to satisfy the until, I need to find a future point that will satisfy phi2. And all the points before that will satisfy phi1. By adding G and wrap it around. So that means I should be able to keep finding continuously to be able to find a future point that will satisfy phi2 infinitely often. And before every such phi2 satisfaction point, I should be able to find before that phi1 is satisfied. So that will be how I interpret it. Of course, you just got to write the quantification to show that. Okay. All right, Harsha, have you got any other questions?
I guess we'll do them after. If
okay, we'll see. If you have enough time, we can take a look at some of the nesting you actually came up with. Yeah, sure. Okay, Jora, go ahead.
Hi, Professor.
Hi.
I had a quick question about translating from English to LTL.
Sure.
So a couple of friends and I were working on this one problem, and I guess I can put the English into the chat quickly.
Sure.
It was, the question was, I must eat at least once before I go to school, right? I'm not really sure how we can formulate this, because it seemed like when we were doing the timeline, then let's say at some point, some arbitrary point in the future, we go to school. Then that means for all states prior to us going to school, for every single state, there must be that we eat, and then the next day we eat, which obviously isn't the same as the English saying. So I was kind of confused as to how maybe we should formulate this.
Let me say, I must eat at least once before I go to, okay.
Or even just, I must eat before I go to school. I guess the two are somewhat equivalent.
Let me think. I must eat before I go to school. Let me see. Also, this also depends on what atoms you are given, right? Because the atom itself can also, let's say, I'm thinking about, yeah.
Yeah, if we did like P is like I must eat, and then Q is I go to school, right? Like Patrick said in the chat.
Sure,
so if we choose those as the atoms.
So let's P is I eat, something like that. And then Q will be I go to school. Okay. one thing that could be a kind of like approximation, which doesn't require until. So let's say this. So let's say if I eat, okay, let's say this. Let's say, basically, I want to say, whenever I go to school, that means the previous days must be such that I actually eat. Let me see if I
Why
can
does it have to
formulate
be the
this.
previous state?
The previous state, but we don't necessarily need that. We can say, let's say, to be careful over here, implies so this one is saying if the next state is such that I want to go to school, then the current state must be that I eat. And that it should always be the case.
Shouldn't it be that I have eaten though, not that I am eating at this state? Because like, can't any of the states before that one?
It could be.
have
So
been
this
you
could be a
eating?
little bit tricky. Yeah, Patrick, I said, yeah. So here, this one here could be the immediately before states, or could be some state before, right? It also depends on what do we really mean by each state. It could be a day, could be 1 hour, could be 2 hours, right? I think formulating into the from English into LTL in general is kind of tricky. Also depends on how you define atoms over here. I think for Tuesday, what you will be given, if you got any, let's say for English into LTL or for LTL into English, maybe just focus more on what we discussed already on Thursday. I think that should be enough. I'll just try to do some variants on them, so it wouldn't be too bad.
So, Professor, sorry to interrupt, but if
go
we're
ahead.
given the English sentence, we're going to be given the predicates that go along with it, correct?
Yes, I don't think, so I don't think on Tuesday, I'm going to ask you guys to write, let's say in the answer box, to say, okay, given this English, write a formula over here. I think I'm more,
Okay.
Unless I change my mind, I'll let you guys know so you can get a little bit more prepared. But I think it's most likely I'm going to possibly give some English similar to what we did on Thursday. And then I would say for the following option, which one more accurately capture that sentence? That could be one. Or vice versa. I can say I give you the LTL, and then I'll say for the following English sentences, which one more accurately explain the formula? Either way.
Okay, that makes sense. And I mean, I know that you mentioned before that we didn't really touch on the next state with respect to the topics that we talked about from test one or test one onward. So in this sense, I guess it does kind of make sense that you can use the next state. So would that be something that we can still like expect to be able to call on for this test, like in this sense?
Yeah, I think So I think for simple use of next state like this, I think that should be that could be expected. I'm not saying there might be on the test. I think some simple manipulation for the next operator. So now that we actually already talked about, given some new nesting, how can you figure out its formal meaning? I think expecting something like this should be reasonable.
Okay, and you said like any kind of LTL or any kind of English sentence that we want to convert to LTL will be some variation of what we kind of did in class already,
Yes,
not necessarily.
Maybe the nouns a little bit different, maybe the pattern are slightly different, but I should be around the same level. I wouldn't give you something that's gonna nest for too many times. Yeah, at least not
okay. So those are kind of the ones I was practicing.
Yeah,
that's good to know.
I think my mindset for written test 2 is a little bit similar to written test 1. Since you guys were only first exposed to until release, week until, and kind of formulation only for the first time. So maybe for written test 2 wouldn't go too harsh. Yeah, maybe the more advanced will come maybe later in the exam.
Okay.
So worry one thing at a time. So for Tuesday, just make sure you understand the example in the test. In the lecture, you should be fine. Yeah.
Okay, fair enough. I did actually have one follow-up question regarding just like some English semantics. So for example, the word sometimes, right? Like let's say if it's I don't know, I sometimes watch a movie on the weekend, right? That is a little bit tricky to formulate into LTL because I guess like I couldn't figure out one exact way of doing it, but there was one that I kind
of because the future operator is not really sometimes. You just say at some future point, and it's only one time, right? So Yeah, I would say any
Because sometimes to me implies that it could happen or not happen, but future means that it's going to happen, but just
yeah, exactly. So I would say, yeah, if you really cannot find something that's really corresponding to what we learned in the class, you don't need to worry. Of course, you can always double check with me, but for sometimes I don't see it's really corresponding to what we learned.
Okay, that makes sense. Okay, I think I'm good for now. Thank you, Professor.
No problem. Let me monitor the chat very quickly, and then I will point to the next one. Bear with me. Okay, I guess just some example there. Okay. Yeah, I think whether to use the week until or the release, some tips, which we maybe briefly talk about on Thursday. So if you go to the summary table over here, sorry, the summary diagrams over here. So I would say you will use the week until if you want to allow the possibility of the phi 1 being continuously true, which means phi 2 never becomes true. So if you really want to have allow that possibility, in that case, you should really use the week until. Otherwise, if you don't want to allow that possibility, you only use the until. And then for the release, you want to think more about whether or not you will require the phi 1 and phi 2 to be true simultaneously. In that case, you may have to use the release. And of course, you want to make sure the order of the two formulas should be put correctly. Okay. Okay. Okay, let's now take a look. Chidalu, go ahead.
Hello, Professor. I just wanted to know if there was some algorithmic kind of strategy in formulating like LTL formulas and
Okay.
you know, like in all state. Like for example, given an arbitrary LTL formula, like I want kind of strategy to formulate it into that, you know, kind of for all I, that kind of form.
I think, yeah, so roughly speaking, okay, I kind of see what you mean. So let's say this. Yeah, in a moment.
And do we start innermost? Do we start outermost? Like
you should start with the outermost. You should. That'll be the first principle. So let's say, for example, right? Let's just say for one example, let's say you got S0 satisfies, I don't know, let's say G, F, and then let's say you have maybe again G, phi 1 implies F phi 2. Okay, let's say, for example, okay. So you will go from outermost to innermost, usually. So here, first of all, for this one here, we know it will be for every pi, and then pi should be starting from S0. And then the outermost will be this one here. So overall, it's more like a continuously pattern. So this one here will be something like, okay, so for every I larger than or equal to 1, and then like that, and the F over here is going to be the remaining part. So this here comes the important part. You have to think about this part here is going to be the body of this for all. So that means you may have to reuse the I. So whatever I you're referring to, it might be reused again over here. Okay. And then let's say for here, you're going to say there exists. So now I'm going to say J. So here I might say J larger than or equal to I. Right? It's kind of relative to the for all up here. And then we're going to say, and then for the future one is going to be this one here. Okay, just one here. And then this part over here is going to be some implication. Okay, so this part here would be the G. And this part over here would be the F. Are you okay so far, Chidalu?
Makes sense.
Okay, so basically right now, so here for G here, you want to say for every, of course. So now we have used I and J, so this will be for every K, and K should be larger than or equal to, it should be relative to the J. And then you want to say pi, okay, pi 1. And this one will be, they exist. I'll just use a different one, maybe L. So L larger than or equal to J, and pi L satisfies phi 2. So you asked about some algorithmic like a strategy. I think that is more or less. Of course, it definitely can be done mechanically if you write some program to translate it. So you want to think about, you always go from outermost into innermost. And then for every one of them you want to apply, think about what should be the corresponding quantifier. And then once you have some nesting over here, the starting point over here should be relative to the previous dummy variable.
Yeah, this works really nice, and I really understand this for the urinary LTL operators. But like, how does this work with the what's it called?
Until operator? It will be very similar, because let's say if somehow you're nesting until, let's say within some global, right? In that way, you can think about here, rather than larger than or equal to 1, it's going to be larger than or equal to whatever that dummy variable is. So let's say this. Let's say we have one example here. Let's say if I say S0 satisfies, and then we can, let's say future, okay, future, and then phi 1 until phi 2. Okay, so this one is really saying at some future point we must have this, right? So here what we can do is again, outermost will be, so let's say for every, let's do the satisfaction first. So we say for every pi equal to S0 and etc. And then let's say future here. And over here we'll say there exists some I. And then I larger than or equal to 1. And now we get to this part over here. Okay. So this part over here is just going to be, the until operator. So that one there is going to be there exists J. Okay. And then you're going to say J larger than or equal to I. But here, larger than equal to I is really larger than equal to 1. So it turns out this particular pattern here, this doesn't seem to be very necessary, right? Can you see my point? Yeah. So it really depends on how the pattern was given, and then you just have to gradually, put a nesting of the logical quantifiers.
Makes sense.
Okay, maybe you can give a try on something you are thinking about to see what the formulation should be, and then maybe we can take a look at some point.
That makes sense. Okay, thank you.
Okay, no problem. Okay, let me see. Patrick, go ahead.
Hi, Professor.
Hi.
So in class we did examples of English to LTL, and we kind of touched upon the majority of operators. So out of the ones we didn't really talk about, like we didn't explicitly talk about the next state and weak until and release. And I know there's a little section where we talked about why is weak until not okay in this scenario. So I guess my question is kind of for the test on Tuesday, are we expected to be able to kind of take an English sentence and determine whether or not weak until or release works? Because we never did examples, and I was wondering if it is expected of us, could we maybe do an example or two of that?
Yep, it's possible.
Because I was kind of in my studies, I wasn't really able to come up with a suitable sentence that.
No, I agree. It's definitely a fair request. How about this? We do. I don't really have some very precise example in my mind. Let me work on this. I can release this example, and then I'll put that and then put some explanation for you guys to actually.
Thank you.
Okay, so I would say
that would be great.
Yeah, no problem. I can do that. especially on release, I'm sure.
Yeah, and even weak until feels a little tricky because you like I don't really get how that fits in with English. Like I know the definition, but
yeah,
it's not quite crystal clear to me.
Yeah, we can try. Okay, I'll try. Okay,
great,
yeah.
Thanks.
Yeah, I think you know, by the weak until itself is basically just by adding one more case that can be satisfied, which is, you know, for the phi 1 just to be continuously true. I'll think about some. I'll work on an example. Yeah, I'll get back to you guys. Yeah, early tomorrow or by early evening tomorrow, I'll give you guys this example. You can take a look. So that you still have time to digest before Tuesday. Okay, very good. And Harsha.
Jorah's before me.
That's okay. You can. I'll take you first, and then somehow appear first to me, okay, and then I'll take Jorah next.
Okay.
Go ahead.
Would an example of release be something like this? The pot remains on the stove unless it is removed by someone.
Until it is removed by somebody.
Or until it is removed by someone. Yeah.
Wait, or it could be that when somebody taking when somebody is trying to take that pot away, that action should really release the pot being on the stove, right?
That kind of confuses me.
Well, the reason is because the pot can't remove itself. A human would have to.
Yeah, so basically, I think that, again, so if we go back to the definition, this is why this part formulating natural language into LTL is actually kind of tricky. So if you look at that here, the really critical bit about using release is really over here. So you want to make sure the point that phi 1 is trying to release phi 2, they should be true simultaneously. And
no, I'm sorry, I didn't mean weak. I didn't mean release. I meant weak until. So sorry if I said that. Sorry if I confused everybody. I meant weak until.
So no, I think a release is also important. I mean, release over here, of course, require both conditions should be satisfied at the point that is released. But if you say for weak until, that part there, it doesn't require the kind of the phi 2 to be sorry, for phi 1 to be really satisfied. Let's say this. Let's go back here. Okay, again, diagram might help the most. Yeah, over here. Okay, so here, if you say until and weak until, they are really almost the same, except that you got this one more case, which can be satisfied by weak until. So you want to think about in your real life scenario that you want to formulate, do you actually allow this particular condition phi 1 to be continuously true? If you do allow that, in that case, weak until should be used rather than until. And when you want to distinguish between until and also release, you want to think about when you try to somehow having these two conditions, should they be satisfied simultaneously? If you think they don't really need to be, or this one here can be satisfied not at this stage, in that case, until should be chosen. Otherwise, if they should be satisfied at the same time, then release should be. Just by according to the definition. I'll try to find out maybe some more example about release and weak until. I think these two are maybe our weakest point at the point. Okay. Asha, can I answer your question or not?
No, I'm still confused which would be the appropriate one to use, unless you're not sure as well.
You mean until and weak until?
I think it would have to be weak until, because if you don't remove it, it stays because it's an inanimate object and there's no apparatus to remove it.
So here, what's phi 2? Phi 2 is a pot is on the stove, right?
No, I think phi 1 is the pot is on the stove, and phi 2 is the pot is removed.
Yeah, so the pot should be on the stove until somebody remove it, right? So here, so we shouldn't really use weak until, because the pot should not be on the stove forever.
No, but it will be if we don't remove it, is what I'm trying to imply.
Well, it also depends on what you want to model, right? So I presume you wouldn't put the pot always on the stove, right? At some point, once you have boiled your water, you should really take it out and then put it somewhere on the tea table, right? Not always on the pot.
Yeah. But I'm saying if someone forgets to remove it, it will remain, right?
Well, it doesn't have to be someone forget or not. I mean, it's really about where the pot should be. We expect the pot should be only on the stove while we're boiling the water, and then once somebody actually try to turn off the button and then try to take it out, the pot should be removed, and we shouldn't really allowed the pot should be there forever. So this scenario here should be forbidden. So that's why we can tell it should not be the case.
Sorry, but then I'm confused a bit. Sorry for jumping in. I'm confused how release kind of plays in there, because that doesn't that kind of imply that the pot is both on the stove and has been removed at the same time?
Yeah, that's kind of what I mentioned a few minutes earlier. But I would say, let me work on some example, and then otherwise here we're just thinking aloud together. They wouldn't be conclusive. So I would say, let me work on some example and then I'll release them. But release, of course, the principle will be these two should be true at the same time. If you think that's a must condition for the example you're formulating, then of course you should really use the release. That one cannot be satisfied by until directly. Okay, Jora, go ahead.
Hi, Professor. So for the model that we're going to be given for written test 2, would you say it's going to be something similar to written test 1 in the sense of like the number of states?
Yeah, number of states. I would say I forgot how many states were there. Was it 5? About 5.
I think 5 or something like that.
Yeah, I would say.
Sorry, go ahead.
Around that range, 5 or 6, maybe around 5 or 6.
Okay, yeah. So okay, that makes sense. Okay, thank you.
And of course, make sure you can also, let's say, given the LTL textual description, you can visualize what the diagram should be. I think that's most likely what you will be given, like in written test 1.
Oh, so we'll still be expected to make the state diagram from the actual.
Yes.
Okay.
Yeah, but that one I'm pretty sure you know how to do it, right?
Okay.
Yeah.
Sounds good. Thank you.
Sounds good. All right, guys. Any more questions? Any more? So I think what I owe you guys by the end of tomorrow, or if not earlier, will be some clarifying example for using we can tell and also release. Okay, but I think I think this is really tricky because you have to be very choosing one or the other. You really have to know whether certain condition can be allowed or not, right? As I said, if you look at the formal definition, it's very clear, but which one to be really used for some real life scenario is tricky. I'll try to maybe do a little bit search myself too to see if there's some example to use. Okay, and I'll get back to you. Okay. And Jora, question.
Sorry, I'm looking through my notes again. Just got a really quick one. So the is the English that we're going to be getting for the English to LTL going to be like very clear? Like for example, the one that you gave over I smoked until I was 22. I think that kind of makes sense. That it's after you're 22, you're not smoking anymore. But for example, like one where it says I always study hard before a test. That's kind of ambiguous as to do you study hard after a test? Do you study hard how far before a test?
Yeah.
So I'm not really sure how it translates in that sense.
I think I'll definitely try to be as clear as possible. Usually I try to review the question myself and really try to think, if I were to really compare this and then formulate the formula, is there another way to formulate it? Also especially compare with different options. That's what I would try to do. And of course, if you really want me to clarify a bit in the test, I can try, but I believe what I will put on the test itself will be quite clear, I believe.
Okay, and then like on the test, you could, for example, you could have a case where it's like an English sentence and you can have multiple choice of which one of these models the sentence correctly, and there could be multiple that accurately model it. That's something I haven't decided yet. It could be that there's only one that's the most accurate you have to choose. That could be one. Or it could be that what can be acceptable formulation. Maybe they have some different boundary cases, but they are still within the acceptable range. So it could be either one. But the question itself would be very clear to say, either you have to choose all the acceptable formulation, or you have to choose the most accurate formulation. Yeah, something like that. Okay, that makes sense. But generally for English sentences, there can be multiple ways to formulate it in LTL, right? Yes, there could be. Mm-hmm. Okay, gotcha. Thank you, Professor. All right, Harsha?
You said just before this about drawing the state graph. I I don't have access to test one, so I haven't seen what you mean by that. What did you mean by that?
Oh yeah, sure. That one there, yes. Okay, give me a moment. It's very easy to illustrate. So if you go back to the lecture notes for model checking, let me show it to you. So you want to go to when we first talk about the formulation of LTS. Okay, this is not here. Sorry. Okay, going too far. Oh, there we go. Okay, like this. So I might say I give you a model like this, so which contains the states, transition relation, and the labeling function. I might just give you these three, and then you're supposed to figure out this should be the graph.
Okay, and then we answer the questions about
then you
the
answer a
logical
question
statements.
like this. Oh, sorry, not here. Like yeah, something like this, right? You might just give it a formula over here. I would say, okay, now use the diagram you visualize and then answer the question. Yes.
Okay.
Okay, good. All right, guys, any more questions? And Patrick.
I don't want to take up much more time, but is when you said that some translations of English to LTL may be acceptable, like is there a way that we can kind of make that less ambiguous? Like like it can be close to correct, but some people may interpret it in different ways.
Yeah, I think in general, this is a very tricky thing to do. I will definitely try my best to really phrase the problem that you have to formulate as clearly as possible. Yeah, I'll try my best to formulate. Of course, how you interpret or how you read it during the test could be a little bit different, right? I'll try my best, and then if you still want me to clarify, if I could do it, I will say, okay, maybe this is not what you're thinking. This is what you should think instead. Or I might just say, maybe read the question more carefully, and you can find out the answer. Either way.
Okay, thank you.
Yeah. Okay. Sounds good. All right, guys, thank you for coming. And then I will see you on Tuesday. Be there in time. And don't forget, if you have time, do really try to verify your PPY and do a mobile and easier login. So you don't have to waste any time doing it. Make sure you bring your sketch paper. All right, you will need it. Yeah, any question you might have, feel free to email me in general. I'll try my best. Otherwise, you can feel free to also come to my office hour on Tuesday. But could be also you have to compete with your colleagues from 3342. They also have a test on Thursday. But anyway, I'll see you guys.
Can we get priority on that by any chance?
I can give you guys priority. Yes, I can do that.
Thank you.
All right.
Sir, can I just ask one quick question?
Yes, go ahead.
Are we to just focus on model satisfaction, not path satisfaction for this test, obviously? Or
I would say if I give you path satisfaction question, that should be simpler because you don't have to consider all the path, right, for the model. So I would say I'm more intended to give you mostly just model satisfaction question. But if I do give you some path one, but just make sure you also need to how to solve them. In some way, just apply the formula to a single path rather than applying to all the possible path, right? So in some way, that should be simpler. So it's possible. I might also ask for path satisfaction. Yes.
Gotcha. Okay. Thank you, Professor.
Okay. No problem. All right, guys, have a good evening. And then I'll see you all on Tuesday, if not earlier. Okay, take care. Bye-bye.